Okay, in this section we're going to talk about partial fraction decomposition. Sounds like a very technical thing, and it kinda is, and sometimes it's not too bad. Decomposition of rational expressions. In your earlier algebra courses, you were given two rational expressions or fractions, algebraic fractions, for example, 2 over x plus 1 plus 3 over x. You had to get a common denominator, rewrite your fractions, and combine those to one fraction. So this is your combined answer here. In partial fraction decomposition, we're going to give you the combined answer like so, and you're going to break it down into simpler partial fractions. So it's kind of like you're going from the answer back to the problem. Partial fraction decomposition of the form f of x over g of x. F of x over g of x is not a proper fraction, a fraction with the numerator of lesser degree than the denominator. If it's not a proper fraction, then divide it out. Do long division or synthetic division and divide f of x by g of x. In other words, this one, since you had x to the fourth and x squared on bottom, this was divisible by the denominator. So they went ahead and did the long division, and they got this part, but they had a remainder of 14x plus 6. So this is what we're going to have to decompose. This is the part you're going to have to do the decomposition on. This stuff will just be listed in your answer, but this will be part of the decomposition. We'll look at an example like this. Then apply the following steps to the remainder, which is a proper fraction. Now remember, a proper fraction is one whose numerator is of lesser degree than the denominator. Factor the denominator g of x completely into factors of the form ax plus b to the power of m, or quadratic forms that are irreducible, and m and n are all positive integers. For each distinct linear factor, the decomposition must include a constant, so we're going to use just a capital letter to represent a constant, over that linear factor. If you have repeated linear factors, for example, ax plus b to the second or ax plus b to the third, for each repeated linear factor, the decomposition must include a term for each power walking its way up to the highest power you need. For example, if I had ax plus b to the third, I would have to put an a over ax plus b, a b over x plus b squared, and a c over ax plus b to the third. Walk your way up to the highest power. For each distinct quadratic factor that's not reducible, not factorable, the decomposition must include a bx plus c, a linear combination, for your numerator. For each repeated quadratic factor, the decomposition must include the terms, so on. So you have to walk your way up to the highest power, just like you did with linear factors. Use algebraic techniques to solve for the constants in the numerators of the decomposition. And I'm going to show you how to do that. We're going to start off with a really easy one. The denominator is already even factored for us, so we don't have to really do any hard work on this one. If you were to multiply everything out on bottom, x squared minus x, your power of x on top is less than that on bottom, so this is already considered a proper fraction, so no long division is needed. So since we have linear factors in the denominator, you have an x and you have an x minus 1. To do the partial fraction decomposition, we're just going to say that this is equal to a constant over an x, plus b, another constant over the x minus 1. Now, I am going to, since this is an equation, you notice I put an equal sign in there. I'm going to multiply through by the common denominator, x times x minus 1, and clear those fractions out. So if I multiply everything by x times x minus 1, those completely cancel out and leave me just 3x minus 1. And this one, the x's cancel out and leave me a times x minus 1 plus b times just x. All right. So what you can do to kind of get find your a and b, finding a and b is what you're trying to do here. So what I'm going to do, I'm going to let x equal 0. I want to let it equal something where it'll make that factor equal 0 right there. So I'm going to let x equal 0. Let's see what we get in our equation if I let x equal 0. 3 times 0 is 0 minus 1. If x equals 0 over here, 0 minus 1 is negative 1 times a, so negative a. And plus b times 0 would just go away. So my equation is negative 1 equals negative a. So that means 1 is equal to a. So I found my letter a. So let's do the same process over with the other factor. What number would make x minus 1 go to 0? Positive 1. So if I let x equal positive 1, let's see what happens. 3 times 1 is 3, minus 1 would give me 2. If I plug in a 1 here, 1 minus 1 goes to 0, so this whole term becomes 0. And then b times 1 is just b. So b is equal to 2. A is equal to 1 and b equals 2. So the partial fraction decomposition is going to be 1 over x. So a was a 1, so 1 over x plus b was a 2 over x minus 1. So this is the partial fraction decomposition we are looking for. In other words, if I were to get a common denominator and add these two fractions together, I would end up with 3x minus 1 over x times x minus 1. Let's try another one. I have another proper fraction here. Notice that my numerator is of lesser degree than my denominator, but the denominator is not in a factored form, so I need to try to factor it if I can. Two numbers that multiply to give me negative 3 but add to give me negative 2. I believe I can factor this one. X and x minus 3 plus 1. Okay, so we have two distinct linear factors on bottom. So we're going to do the same setup as we did on the last problem. A over x minus 3 plus b over x plus 1. Now, if I multiply through by the common denominator, which is just x minus 3 times x plus 1, I would be left with 5x minus 3 equal to a times the x plus 1 plus b times the x minus 3. That's what we would be left with if we multiplied through by the common denominator. So first thing I'm going to do, I'm going to say let x equal 3. Because I'm looking at this problem here, 3 would make that a 0. So let's see if that helps us in this problem. So if I let x be 3, 5 times 3 is 15. 15 minus 3 would be 12 equal to, if x is 3, 3 plus 1 will be 4a. And 3 would give me a 0 here, so all that would go to 0. 12 equals 4a, so a is equal to 3. Then let's let x also equal negative 1. This factor would be 0 if x was negative 1. So let's try that and see what happens. If I let x be negative 1, that is negative 5 minus 3, that'd be negative 8. If I let x be negative 1, this would all go to 0. But negative 1 minus 3 is negative 4, so negative 4b. So b is equal to 2. Now just go back and substitute, and that's going to be your partial fraction decomposition. I'm going to do this in different colors so you can see it. A is 3 over x minus 3 plus 2 over x plus 1. That's your partial fraction decomposition. In other words, if I were to add those two fractions together, they would give me this combined answer. Let's try one more. This is also a proper fraction. If we were to multiply everything out on bottom, we would have x to the third. On top, we only have an x, so that lets me know this is not improper. This is proper. The denominator is already factored. But we have one little distinct difference now. You have x plus 1, you have an x plus 2 squared. So we have to walk our way up to the x plus 2 squared. So the partial fraction decomposition would be an a over x plus 1 plus b over x plus 2 plus we have one more, c over the highest power, x plus 2 squared. Now, in that setup, if I multiply through by my common denominator, which would be x plus 1 times x plus 2 squared, I would end up with 2x equal to a times x plus 2 squared plus b times x plus 1 and another x plus 2 plus c times just the x plus 1. Okay, so let's go through some methods here to see how we can extract a, b, and c. So the first thing I'm going to do, just like we've done in the previous examples, I'm going to let x equal negative 1 just to see what happens. So if I let x be negative 1, on the left side that's going to give me 2 times negative 1, which is negative 2. If we put negative 1 into this equation, that's going to give me 1 squared, which is just 1a. Negative 1 would give me a 0 in this term and a 0 in this term. So those two terms, b and c, dropped out. So we were able to find a. A is negative 2. Let x equal negative 2. So if I let x equal negative 2, 2 times negative 2 is negative 4. This whole term would go to 0. This whole term would go to 0. But on this one, negative 2 plus 1, that's negative 1c. So c is just going to equal 4. However, you can see I have not found b. I have not been able to find b. So what I can do is this. Well, let's start using our terms. Over here, we have 2x is all we have. If I were to multiply these terms together right here, x times x, then I would get an x squared term that goes with b. Also, if I were to square out x plus 2, I would get an x squared term also with a. There's no x squared term with c. So let's just compare our x squared terms. On the left side, there are no x squared terms. All you have are x terms. No x squared terms, so 0. X squared, you'd get an x squared times an a, so we have an a plus, right here with b, if I multiplied x times x, I would get an x squared with b, so b. And we also said we didn't have any x squared terms in this last one. So we already know what a is. A was negative 2, so 0 equals negative 2 plus b, so b must equal 2. So there's your partial fraction decomposition. So if we went back now and placed our, this would be negative 2 over x plus 1 plus 2 over x plus 2 plus